Um, this is something I've been working on for the last year with Juan Sosa, who is here. Uh, the structure of of my talk. First, I'm gonna talk about the motivation. I'm gonna talk about a very important paper. Then I'm going to propose or use a model to represent or to estimate the capability to influence of the individuals in a social network, specifically in an online social network. Then I'm going to model the diffusion of an idea in an online social network in order to perform several simulations. And well, I conclude. Okay. Uh, this paper called Influential Networks and Public Opinion Formation is very important because in that paper, Watts and Dots try to study how the characteristics of the nodes of online social networks affect the diffusion of an idea, or how far can an idea travel through the network. So what they did was that they assigned a threshold to each node, for example, a value from 0 to 1. So if my threshold is 0.3, that means that if the 30% of my neighbors start sharing an idea, I will start sharing it. So they say that I am activated. But they characterize the individuals through these thresholds and perform the simulations in simulated networks. So what I'm going to do here is to change the networks. Well, we are going to simulate the networks, but in a more realistic model. And we are going to change the idea of the thresholds by an idea of two main parameters: the capability to influence of each node and their influenciability degree. There's another important parameter, which is tau, which represents the similarity between the ideas of the individual I and individual J. Well, the model. I'm going to use a known model with a model called the latent space projections model, proposed by Hoff, Raftery, and Hancock in that year. So let's say we have a graph in which there is a link from individual I to individual J if I influences J. And this variable will be 1 if I influences J and 0 if not. So we are going to model these variables using these parameters that are very important. The first one is the capability to influence of I, this one, and these two are a vector of latent characteristics of individuals I and J. So those vector contains characteristics that we can't measure. We don't know what they represent, but we know that they have information that is important or that has an effect on the probability of I influencing J. So that's the model, and we are going to reparameterize the model. So we write U as a product of a scalar and a unitary vector. So this unitary vector theta represents the orientation or the direction of the node I in a political spectrum if we are talking about political influence. And I will be a scalar. So the other parameter is tau, and we will define it as the dot product between the direction of individual I and individual J. That makes sense because if their directions are close, that dot product, which is the cosine of the angle between them, will be closer to 1, and if they have opposite positions, that tau ij will take the value -1. Okay? So if I replace that reparameterization in the model, we can interpret easily the model. So, for example, if individual I and J have opposite opinions or positions in or characteristics, this term will have a negative impact on the probability of I influencing J. But if they have similar ideas, that term will have a positive impact on that probability. And the impact will be scaled by this in score of J, this one, which that means that if J has a big or a large value on that parameter, J will give a lot of importance of the position of I in a political spectrum when we are considering the probability of I influencing J. Um, well, that's the model. Now we are going to estimate the parameters through Markov chain Monte Carlo, specifically the Metropolis algorithm, and that will allow us to estimate not only every parameter of the model, but any function of the parameters, which is very useful in this case because we are reparameterizing the model, so we need to estimate those functions of the parameters. Um, and it will also allow us to measure the uncertainty associated with the estimation of each parameter. Well, now we are going to use real data. This is a retweet network. So the context is that the last year in November, the government of Colombia proposed a tax reform. So I sampled between the tweets that mentioned that tax reform, and I put a link from I to J if the Twitter account J has retweeted I. Mm, this is the network. So the first thing that we see, well, it has 634 nodes. And the first thing that we can see is that it's composed by two groups. The one in the corner, in the top right corner, is the one that supports the tax reform because there's the president and some senators of the same political party as the president. And in the other corner is the group that rejects the tax reform because, well, there's the senators of the political party that declare himself in opposition. So these are the most popular Twitter accounts in that context. And here we can see the estimation of the capability to influence of each of the most popular accounts. Though you can see senators, the president, and here's the director of the Parliament of Colombia that deals with everything about taxes, so it makes sense because it's a tax reform. Here is the network, but assigning colors according to the capability to influence of each individual. And here is the representation or the estimation of the writing characteristics of the individuals. So here we can see that they follow like a really specific. Actually, he only need one dimension, only one writing characteristic to represent the 98% of the variability contained in these two dimensions. And the color is assigned by the capability to influence. And the circles, maybe you can see that. The circles are the ones that support the tax reform, and the squares are the ones that reject. So that space, that latent space, captures the different positions. Here is the tau ij elements with all the combination of I and J reorganized by groups. So first is the group that rejects that supports the reform, and then is the group that rejects it. So you can see that the model captures that behavior of bipolarity. And here in the inner circle, I plotted the direction of the most popular or the individuals with the most capability to influence. And in the other circle, I somebody in the inner circle. So here you can see that is they are organized in opposite positions. Oh well, and now I have estimated the capability to influence and the degree of influenceability of each individual. So I'm going to then be undecided again and then rejecting it. So we are going to model. This is a different approach from what we have seen so far. We are not going to use simulations on several scenarios on which we measure the total time that it took the diffusion, as we are modeling times, and the proportion of the individuals that end up in the biggest group, the supporters or the rejectors. We consider several scenarios based on factors. The first factor is the capability to influence is unevenly distributed. In this case, this is a gamma distribution. Or the other scenario is with a constant. So everybody. So we have a network composed by a single cluster, another one by two clusters, and in each of those cases, we choose the initiators of the diffusion by randomly or as the ones that the most capability to influence. So we want to test if that changes the reach of the diffusion. So here are some examples. We perform several runs for each scenario. So here you can see how the supporters and rejectors are practically in a tie. But here's another example on which the supporters won, we can say. So just summarizing the results, we latent space, and the variability can be captured in a single dimension. And we found which factors are associated with the richness of a diffusion. Thank you.
Thank you, Samuel. Are there any questions for him?
Hi Samuel, thank you for your talk. It's something a little bit different of we are used to mechanistic models. But I make you more technical question because I try to understand a little bit more about this Bayesian approach to simulate process and epidemics, and I had some difficulty. So maybe in your problem, how robust are the choice of the distributions? Because sometimes you use the gamma distribution due to the asymmetry of the distribution, but at the beginning you use very little distributions. another point use the exponential that is more common for stochastic problems. And so I wonder how robust is your results or this type of analysis when you change the distribution that you use in your statistical analysis?
Thank you. Well, the first distribution, the Bernoulli, well, is if I'm trying to model a variable that only takes values 0 and 1, I think that is like the main option. But talking about the exponential distribution I use for the times, sorry, it's here, yeah. I choose the exponential distribution because it gives us some tools that allow us to simulate the diffusions easily. But I haven't explored different distributions, and I also choose it because, yeah, in the context of Markov chains, when you model that, for example, a Poisson process, the time used to follow exponential distributions. But I haven't measured how is my results robust with the choice of the distribution.
Any other questions? Okay, let's thank again Samuel for